Okay, so why don't we start today's topic here? I've actually got my first slide of notes here being an example of something that we've actually learned before. This isn't something new curriculum-wise. So I want to begin with just a classic scenario here. Being a football lover myself, I'm beginning with a football example. Let's say that you have a running back, and the running back is moving 7 meters per second at a certain angle, and he gets tackled by a linebacker who is heavier than him and is also traveling faster than him. And he's going to tackle the other player. This is going to be your classic hit and stick kind of collision, where if I use my hands here, here's object 1, here's object 2. They're going to combine together and keep going. This is very different than the lab we just did, because in the pool ball example, did any of the pool balls stick together? No. Right. But here, the pool balls, only in this case they're not pool balls, they're humans, they will stick together. What we effectively have then is a scenario that looks like this. The mass times the velocity of, say, the running back, plus the mass and the velocity of the linebacker will need to equal their collective masses times by their collective velocity. See how I'm kind of like making my own formula up here? And this is really the hallmark of what makes Physics 20 different than Physics 30. Physics 20, you normally get just given one formula off the formula sheet and you just rearrange it. Physics 30, you kind of have to make up your own formulas, and hopefully this concept makes sense. The mass times the velocity of object A plus the mass and velocity of object B need to equal their combined masses and their combined velocities. Here's the problem though. I have to do this in both the x and the y dimensions though. I have to do it twice. I can't just do it once across the board. I have to do it based on vector analysis. So I'm going to have to sit down to do this because there's a lot of work I have to do here. I think it would be a good idea to draw a picture. So, do you guys know what 250 degrees means in terms of an angle? If I use the standard position version that you use in like math class, you guys are aware that like in math, 0 degrees is like over here. So then 250 means we're talking about someone who's traveling that direction there, right? Because this would be 0, this would be 90, this would be 180, this would be 270. So all the way around to here is 250 degrees. And so apparently the running back is trying to move this way here. Then the linebacker, I'll use another color here, the linebacker is moving at 10 degrees. So 10 degrees, if I kind of get a start going, 10 degrees means he's moving like that way, like this. They're almost going head on, eh? Not quite, but almost head on. And if I were to draw vector arrows proportionally, I haven't done this very well, hey? Because really, this vector arrow should be much bigger than the purple one. Because again, the running back is smaller and going slower, and the linebacker is bigger and going faster. But these two things are going to collide. Our goal is to figure out when they combine together, which way are they going? Sound good? So the first thing I'm going to have to do then is break each of these vectors up into their x and y components. So I'm just going to start by doing this. I'm going to take this first vector right here. And, well, why don't I draw it with the axis like this? Let's find an x and a y component. So this can be his momentum in the x direction, and this can be his momentum in the y direction. I'm going to calculate just how much momentum there is in the x and the y. On the hypotenuse, this was the running back, right? So this was 70 kilograms traveling 7 meters per second. How do I solve for the x and y components? What do I need to do? Trig. Sine or cosine? What's the only thing I'm missing, though? I don't actually have an angle on here yet, do I? What angle should I use, and where should it go? You don't have any great ideas? Yeah, if you were to put 70 degrees right here, that would be a really good idea. And the logic behind that is it's 180 degrees to the axis right here. So it must mean there's 70 degrees more right there. That'd be a great idea. Now, once you get the hang of how this looks, I can actually calculate the momentums pretty quickly. X is always cosine. So I'm going to go 90 times 7 cosine 70 degrees. And then the y dimension will be 90 times 7 times the sine of 70 degrees. So if I want to know the x and y dimensions, I just do the mass times the velocity times the angle. And this first formula that I've done right here didn't account for any angles yet, hey? So that's why I didn't really want to jump into this first formula just yet. I need to calculate what these momentums are. So hopefully I do a good job of keeping this somewhat organized here, because organization is really important. I need a calculator. Bear with me one sec here. If I do 90 times 7 times the cosine of 70, I get 215 and change. Anybody else get that? 90 by 7 by cosine 70? I got 215 and change. But honestly, because that value I need to use more later, why don't I just store this as a letter? I find that useful. So I'm going to store this as letter, say, A. The x momentum is now letter A, and I'll store it in my calculator. You guys know how to store a number in your calculator? You don't? Okay. If you have a typical graphing calculator and you want to store a number, right above the on button is STO with a little arrow. You see that? Press that, and it's going to go answer with an arrow afterwards. And then all you got to do is just pick any letter on your calculator. So if you can see, mine are all green. It goes A, B, C, D, like on there. If you press, like, say, alpha math, it'll then make the letter A come up. And if you press enter, from now on, A is that number. So I'm just going to store this number here, the 215 number here, as A. And I'm going to do the exact same work, 90 times 7 times the sine of 70. I got a number of about 592. So when I did this side right here, I got 592. But again, keeping track of all that's kind of crazy. I'm just going to call that side B. And so that was for the running back. It's x and y momentums. Store as B. Now I need to extend my page here. I need to do the exact same thing for the linebacker. So the linebacker was coming at 10 degrees, and it also had some x and y momentum. So if I were to redraw this out here, this was 10 degrees. Now what's on the hypotenuse? He was, how fast was he again? He was 122 by 8. So he was 122 kilograms, going 8 meters per second. So the same logic kind of applies here. If I want to find the y value, I do 122 times by 8 times by the sine of 10 degrees. And if I want to find the x value, it's 122 by 8 times by the cosine of 10 degrees. But again, rather than actually recording what these numbers are as a numerical value, I don't see much value in writing those down. Why don't I just store them in my calculator as more letters like C and D? So I'm just going to find them real quick here. I got 122 by 8 by sine of 10. And I got one of them being about 169. I may as well store that as letter C. So store that as letter C. And for the last value, 122 by 8 by cosine of 10 degrees, I got 961. But again, I want to save that whole value. I'll store that as D. So, just going to pause for a second there because I know everyone's kind of at a different stage. Does anybody have any questions, though, that you can think of about how I broke the running back's momentums up into an X and a Y momentum, and I broke the linebacker up into an X and a Y momentum? What's my next step? Add or subtract them, right? Which numbers need to go with each other? A needs to go with D. Why? Because they're both in the X dimension, right? So A is in the X dimension, it should go with D. Should I add them or subtract them? Why should I subtract them? They're going against each other, right? because this guy was traveling that way, and this guy's traveling this way, right? So I'm going to need to take A and D and subtract them. And I'm going to need to take C and B. And what should I do with C and B? Subtract them because they're going opposite directions, right? And what I'm really doing is I'm calculating my net amount. And I know it doesn't seem like it's this first formula, but it really is. I'm taking the mass and velocity of the running back and the mass and the velocity of the linebacker, and I'm adding them. But I'm really not adding them. The only reason why I'm subtracting is due to the fact that like one is going a positive way, one's going a negative way. But like it still works out the same. We just have to assign something positive and something negative. So why don't I draw like a net amount? I'm going to draw my net amount in the x direction. So in the x direction, I believe the bigger of the two values is going to be this d momentum, because it was like 960. So why don't I take d and subtract a? That will tell me how much net x momentum we have. And if I want to find my net momentum in y, I just need to know which one's bigger again here. It looks to me like b was 500 something I wrote down, and c was 169. So why don't I go with b minus c? I'm just going to calculate some new values here. This one's b, by the way. So if I take d and minus a in my calculator, I got this. And again, I'm going to store these numbers, but I got 745, something like that. And I may as well just keep storing these values so that I never lose track of them. So I'm going to call this one now E. So I'm going to store this one as letter E. And if I take B and minus C, I have a difference of 422. And again, I should save all these numbers in my calculator, so I'm going to store this as F. Anybody have any issues with being able to add and subtract those? Yeah. Yeah. I think it's best to think about that at the end, because that's what I'm going to do next, is now that I just know the net difference between the two, I just want to consider like which direction wins out. Right? And it looks to me that in terms of like the side-to-side direction here, it looks like D, which was going to my right, wins out against A, which is going to my left. So my net vector E is going this way here. This is E left over like that. And then for the other direction, who won between B and C? It looks like B actually had more momentum than C did, right? So when I try to consider who wins out there, B was 592, C was 169. So it looks like this thing is going to be going down. So then that was where F goes. One last question here. When I solve for E and F, though, these are the momentums on the X and Y axes. I don't actually care about that, though. What I really care about is the hypotenuse. I now think I have a picture of what's happening. One guy was going this way. Another guy was going this way. And when they finish, they were actually going to travel that direction when they're done, stuck together. If I want to figure out this final hypotenuse right here, just use Pythagoras' theorem. So do E squared plus F squared square rooted, and that'll give you your hypotenuse in momentum units. And really, that's what this formula up here started with. We then took our initial momentums, and we're now starting to figure out what our afterwards momentum is going to be. But now we're doing it on the hypotenuse. So I'm going to take my E value, square it, add my F value squared, square root the whole thing. On the hypotenuse, I have a momentum value of 857 or so. But that is momentum. That's kilograms meters per second. And that was the momentum on the hypotenuse. I believe we were asked to solve for the velocity, though, that they were traveling. So how do I change momentum into a velocity? But what mass? The combined mass, which is why in this formula up here I pointed out you need the combined mass of both of them because they're tackling each other, right? Well, one's tackling the other. So the combined mass looks like it's 212, I think, kilograms. So if I divide this by 212 kilograms, I should get their velocity. So divide by 212, and now we're done the question. I got a combined velocity of 4.0 meters per second. Good question. I'm going to just give a little wait time, though, for everybody. But you're right, we should do that, too. This is one of the downsides to doing the lesson altogether, though, is that some kids are like ahead of me, some of you are behind. So I'm just going to pause for a second in case you're someone who's still a little bit behind. Okay, one last question here then. We also may be asked to find this angle right here. If you're asked to find the angle, it's pretty straightforward. You just do the tan inverse of your opposite and your adjacent. So in this case, my opposite was side F, and my adjacent was side E. So if you do a tan inverse of F over E, you'll get this angle right here. That way you know what angle they were traveling at. So last step, inverse tan. This is also why it's really nice to save all your values in your calculator. F over E. I've got an angle of, with 2 sig digs, 30 degrees. F over E. Because F is going to be your opposite, and E is going to be your adjacent. So I calculated 30 degrees. However, that's not really going to work, though, because that's 30 degrees like below the x-axis. All the way around the circle will actually be 330 degrees. So I guess that would be the best possible answer you could give. 4 meters per second, 30 degrees below the axis, which is 330. Questions? Mark? Yes. Yeah. That's what I did. Yeah, right. I just figured out who was bigger than who, right? So since up was bigger than down or left was bigger than right, I just subtracted them in that orientation. There's no one right way of doing it. Hypothetically, let's say that you subtracted them the wrong way around, you would just get a negative number. It wouldn't make a difference then, right? Because if you did a vector, then just your negative number means you're going down, that's all. So it really doesn't make a difference as long as you understand the big picture. Yeah. You can do that too. Yeah, if you wanted to go 30 degrees south of east, that'd be reasonable. Yeah. I don't know how you'd get asked, like how they're going to phrase the answer, but you seem to know what you need. Hi. You looking for me?
Yeah.
What's up?
Good.
What's up? Absolutely, yeah. You need a pencil, or you need a pencil sharpener? Okay. Here you go. Cool. See ya. Okay. Does anybody else have questions on that one there? Able to more or less follow along? You don't have to do it the exact same steps I do, but if you understand the big picture behind how to solve it, break it up into its x momentum, into its y momentum, add or subtract them, recombine your net values, use Pythagoras' theorem. If you get those big picture things, you can solve what you need to. Yeah, I put 330 degrees. The reason why is that it was 30 degrees, but that's 30 degrees like below the axis here. So the long way around the circle is 330. Okay, I want to move on. Sorry, this is one of the downsides to doing the lesson together, is that some of you are like, okay, I'm ready to go, and some of you might be waiting. So that's why I like to record this. I only have a little bit left, actually. There's not a lot of slides in today's notes. What we're discussing today, then, is kind of a continuation, the idea that momentum and energy are quite closely related. There are actually conservation laws for both. We know that there is a conservation of momentum. We also know that there should be a conservation of energy, but really both of these things require an isolated system, right? As long as you have a true isolated system, you're not going to lose, quote, finger quotes, right? You're not going to lose energy, right? Well, some new vocabulary I want to talk to you guys about is the terms elastic collisions and inelastic collisions. And basically the way these work is that if kinetic energy is conserved, you have an elastic collision. Energy is always conserved. We can't really lose energy, right? It just transforms to different forms, right? But if your kinetic energy, the energy of your motion, maintains constant, we consider that to be an elastic collision. Right? What it really means is that the velocity you began with should hopefully fully carry through the collision. But is that probably going to be the case? Well, no, because you're going to lose energy due to sound and heat and light and work done to bend materials. And so the basic idea is, I'm going to skip ahead a slide here if I could. I'm going to skip ahead to my last slide. I'm going to go to this one right here. Typically, if you ever have a microscopic collision, those are elastic collisions. If any of you have done any chemistry, like chemistry 20 or 30, you might have talked about this. Maybe not, I'm not sure, depends on your teacher. But if you had, say, subatomic particles colliding, like, say, electrons hitting each other, you probably are going to conserve kinetic energy. And the reason why is that subatomic particles are probably not going to hit each other and give off sound, or they're not going to, like, warp and, like, bend. For example, this is a really silly one, but let's say that I were to take two objects and have them collide with each other. It's going to be my fist and this sheet of paper. Was kinetic energy conserved? Well, I mean, it wasn't even close to conserved. The paper just like fell straight down. One of the reasons why is that the paper kind of bent around my fist a little bit, right? You could even hear the sound, right? And so when you have what we call macroscopic collisions are like everyday life collisions. We normally lose the energy due to heat, warping, right? When I hit the paper like went around my fist a bit, right? And that is a loss of energy due to work. But if you ever have microscopic collisions, well, those really don't lose energy in those sorts of ways. So I need you to know those terms then, elastic and inelastic collisions. So why don't I go back to the slide I skipped here? We're almost done. I'm only going to do one more example. Did I explain that well enough then? Energy is always conserved. That is always true. We might not be able to measure where energy is lost to outside of the system, but you can't just lose energy. It might have escaped your system, but you can't really lose energy. But you can lose kinetic energy because kinetic energy is changing into other formats, thereby being, finger quotes, lost. And when it's lost, then we call that an inelastic collision. And so here's an example of something we're going to do. It's called a ballistic pendulum. And this is actually what we're going to do in our lab, essentially. Here's how a ballistic pendulum works. You take a gun, for example, and you shoot a bullet at a block. What ends up happening is the bullet lodges itself inside the block, and due to its momentum, carries the block forward. But you notice the block is on this pivot. It's on a pendulum pivot, right? And so what ends up happening is the block swings upwards, and then it's going to fall back down. Does that make sense? That's a ballistic pendulum. And so we can actually use concepts of momentum conservation and energy conservation to solve a question where a bullet comes in, hits the block, and it swings upward. What we're going to do in our lab is actually going to be the exact reverse. I'm going to have a duct tape cannon, and this is going to be an open end right here with a piece of duct tape stuck inside. A little hole in the back, and I'm going to light a match, and it's going to light some methanol, and it's going to cause the duct tape to swing out this way. It's going to cause the cannon to swing back upward because we're going to suspend the cannon from the roof, and we're actually going to see the cannon kind of like have like a kickback rise to it. So why don't I just start the example, because I just have one example here and then we're done for the day. Let's read this one here. Let's say that you have a bullet and it gets fired from a pistol and it hits this ballistic pendulum. So the whole point of it is it's supposed to swing up a little ways. Upon impact, the pendulum swings forward and rises to a height of 0.219 meters above its equilibrium point. We're going to assume the bullet didn't significantly slow down due to air resistance, because let's say it did. If the bullet is slowing down due to air resistance, it's implying that it's not an isolated system. It's implying that energy was, finger quotes, lost. So this sentence right here is a way, I can't draw properly here. Let's do this better. This sentence right here is a way of trying to indicate to us that we have an isolated system. We have two questions. First, we want to figure out the velocity of the bullet as it was shot. And then second, we want to try to calculate the collision as inelastic or elastic. So let me show you how to solve one of these. I'm going to draw a picture again. Here's a gun. And it's going to shoot out a bullet. It's a bullet. But the bullet is going to very quickly become lodged in this block. So here's a block, and the bullet is going to end up lodged inside this block here. Due to the transfer of momentum, is this not basically the exact same as the football player we just did? Right? The one football player tackles the other football player, and they keep going forward together. Right? Is the bullet not going to hit the block, and then they're going to go forward together? But they can't keep going in a linear line because we've suspended this thing from the ceiling, and it's going to swing upwards. And what we've been told is how much swing upwards it has. It's going to increase its height by 0.219 meters. That is a change in height. Well, hang on. If it gained height, is it gaining momentum at that point? What happens when it's gaining height? What's changing? Not its momentum, it's changing its energy. Because when it's in motion, what kind of energy does it have? Kinetic energy. But as the block starts to rise upwards, the kinetic energy was turned into potential energy. And that's what gets us started. We know that at this moment right here, there is kinetic energy in the block and the bullet. But as this thing rises upwards and like kind of kicks backwards, it's going to turn that energy into gravitational potential energy. This is the essence of what makes Physics 30 so challenging. There's no formula on your data sheet that just tells you what to do. You have to have good problem-solving skills and understand that this is where you start. Your mass times your gravity times your change in height came from 1/2 mv squared. Your gravitational potential energy causing the block to rise, the only reason why it rose in the first place is because you had some kinetic energy. That's not a formula on your data sheet. It's two formulas kind of merged together. But I can actually solve for something out of this. Think of the variables that I know. Do I know the masses of all these objects? Yeah, I didn't actually need it though, did I? Because once the bullet becomes lodged in the block, the mass isn't changing. So I can really cancel mass off both sides. Do I know gravity? Yeah, 9.81. Do I know how much height I'm going to gain? Yeah, it told me, 0.219. Well, there's only one more variable left. I should be able to solve for a velocity. Okay. So first I'm going to solve for that velocity. Then we're going to talk about what we've actually discovered, because that's the essence of what we're doing here in this Physics 30 course, is trying to figure out what velocity do we even solve for? Like the velocity of the bullet, of the block, before or after. But first let's solve for this value, because you guys should be able to do that, right? Times both sides by 2, square root. Where's that calculator? If I take 2 times 9.81 times 0.219, square rooted, I've calculated a velocity of, again, I'm going to round this and store it. I got 2.07 meters per second, and I'm going to store this as letter A from now on, just so I don't lose that. So there, I now know a velocity. But again, of what? Yeah. But what's going to end up happening here, though, is as soon as the bullet hits the block, they're now collectively stuck together. Does that make sense? And so as soon as they're stuck together, that stuck togetherness has energy, and that energy swings upwards. So like the mass really hasn't changed, because from the moment at which they become lodged together until the moment at which they're up here, it's the exact same scenario. What we need to figure out, though, you're a little ahead of me, is we need to figure out the instant before they collided. Remember how we did our lab with the pool balls? And we have to know the second before they touch each other and the second after they touch each other. Right. What I think what you're discussing here is you're talking about the bullet before it gets lodged in the block. I'm talking about the bullet is now lodged in the block, and now it's going to begin to move, though. You get the difference between the scenarios here? This is before the bullet has even lodged in the block. I'm not to that point yet. I want to talk about the bullet is in the block, and the block is going to start kicking backwards. And from that moment on, the mass didn't change because the mass of the bullet is inside the block. You are right, though. The mass will change, though, if we talk about the before and the after part of the block actually getting lodged together, though. So I think maybe that actually discusses what my next question was. What velocity do we just solve for? We solved for the velocity of the bullet and the block once they got lodged together. Remember how just a few minutes ago we solved for the velocity of the linebacker and the running back together, stuck together? We now know that velocity, and we know it the second after the collision. If I could redraw out something from earlier today, remember how I was drawing out like a table of values? Where in the table of values we had your time and we had your velocity. And like your time was, say, 0, 1, 2, 3, 4, 5. And let's say that the collision happened in step 3. Beforehand, your velocity was nothing, 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 because it was just sitting there, right? And then afterwards, it was 2, 2, 2. What we have now solved for is the velocity, the second, the millisecond after the collision occurred. And after the collision occurred, those masses are together. Before the collision occurred, the masses weren't together, though. So here's where we can go next, then. This was using conservation of energy. Now we can talk about conservation of momentum for the collision. So let me draw something new here. In our collision, we had this scenario. We had the bullet by itself, and we had the block by itself. And then after the collision was over, the bullet was inside the block. Let's write a second formula about momentum. How much momentum does the bullet have? Well, it has its mass times its velocity. How much momentum did the block have just sitting there? None. Yeah. And how much momentum did it have afterwards? Well, I think we can actually calculate it. It's mass times its velocity. But what's different about this mass right here is that you have to add the two masses together afterwards here, but not before the collision. This is before and after they became embedded with each other. So I'm kind of writing my own new formula here. I'm going to undo that. I didn't mean to write that on there. I'm going to write my own new formula because really, this is the mass velocity of the bullet. This is the mass times velocity of the block, which really we don't even need to care about because it was stationary. And then you have the mass and velocity of both. Well, hang on, I know all this information. The bullet was 0.0149 kilograms. And I did not know the bullet's velocity. The second before it was embedded. The second before the bullet was embedded, I don't know its velocity yet. But I do know the velocity the second after it was embedded. Wasn't that 2.07 meters per second? That's the velocity the second after it was embedded. However, the mass is different now because the mass the second after it was embedded is both of them added together, right? So that's going to be 2.0149 because I have to take the 2 kilogram block and add the bullet together. Well, now I just need to solve for the velocity. So if I divide by the 0.149 on both sides here, I should have an answer. So I'm going to take 2.0149 times by A, because that's what I stored my velocity as, divide by 0.0149, and I got a velocity. What do I get for sig digs here? Always scroll back up, I guess. Looks like 3 sig digs. So I got a final velocity of 280 meters per second. Anybody else able to calculate that 280? Sweet. So let's talk about what we did here, because none of these are really formulas that you can just plug in right off your data sheet. This involved a lot of interpretation and understanding what happened when. Let me do a quick recap. I was able to calculate the velocity the second this box began to move. The second the box began to move, because at this point here, all it had was kinetic energy. But I know that its kinetic energy turned into gravitational potential energy because it rose, and that gave me my first formula. So gravitational energy happened because of kinetic energy the second after the bullet became embedded. And I solved for that velocity using conservation of energy principles, and I found that velocity here. This is the velocity of both the bullet and the block as they are together. Because the second before they're together, the block's not moving yet, right? They have to become embedded for the whole system to begin to move, right? Once I knew that velocity, then I approached it from a conservation of momentum point of view, where there was a collision. This bullet and this block were not collided, and now they were collided. So the bullet had momentum, the block did not. Afterwards, they collectively had momentum. I know the velocity of the collective momentum because I just solved for it. I know the collective mass of both the bullet and the block together. I know the mass of just the bullet by itself. Doing that, I could then solve for the velocity of just the bullet. And there we go. Now, this is what makes the course challenging. Is that, and this is what I really learned after teaching the last class, my Physics 31st semester, is that my understanding is when you guys did Physics 20, you're pretty used to doing a lot of math formulas. But most of the time it was, I give you some numbers, you go to your formula sheet, you plug in all the numbers but one, and you rearrange for the missing number. Is that pretty familiar for you guys? If you get that in Physics 30, count your blessings, because that's very, very, very rare. Most of the time you're going to be given a crazy convoluted scenario, and you have to understand how to make your own formulas, how to like merge them together. And the example I like to give is, any of you guys ever done one of those like escape rooms where you like get locked in the room, you have an hour, and you got to try to find the way out of the room? And like there's a clue that gets you a key, and the key opens a safe. And inside the safe, there's a new clue, and that clue gives you a punch code to a iPad. And then you get into the iPad, and the iPad has the next clue, and it gives you another. You guys have done these before? You know what I'm talking about? You have to approach physics in that sort of scenario where it's a series of puzzles where using these formulas gets you this, and now you can use these formulas over here, which gets you to here, which, and you have to piece it together yourself. And that's what makes it challenging. So that's one of the reasons why I like to give you guys lots of different lab scenarios, because it challenges a different side of your mind. If you just want to do just like raw algebra practice, that's not going to be enough if you want to do well on some of the questions you're going to be asked. So, anyways, I'm running out of time here. I hate to kind of move on, but does anyone have any questions they can think of right now? Okay, so let me do a quick recap here of what we accomplished then. Today, we talked about 2 new words. Oh, I didn't even finish the question. I need to do more. It said elastic collision and inelastic collision. I just realized I didn't even finish the question. I only did part A. We calculated the velocity of the bullet. The second part is to figure out whether it's elastic or inelastic. Let's make a prediction. Do you think this collision is going to be elastic or inelastic? Why are we losing energy? What are we going to lose energy to? Hey, come on in. Probably sound. Probably heat. Right? Stuff like that. Thank you. Thank you. See you later. Hi, Jared. So what we have to calculate now is whether the collision was elastic or inelastic. Here's how we do that. Sorry, I didn't realize I didn't finish the question. The collision involved this scenario here. Know how I did mv equaled mv? I now need to calculate whether 1/2 mv squared equaled 1/2 mv squared. I got to calculate whether this initial energy right here fully transferred to this one over here. But here's the good news. It's not that hard. Do I know the mass of the bullet? Yeah. Do I now know the velocity the bullet was traveling? Yeah. Didn't I just solve it? It was 280. Do I know the mass of the bullet block combo? Yeah. Do I know the velocity of the bullet block combo? Yeah, it was 207. Now here's what makes this different though. We're not isolating for a variable. We're trying to see whether if you get 8 on this side of the equation, you also get 8 on the other side of the equation. If you do, then it was conserved. So why don't I leave that for you guys? That's actually not that challenging to do, right? All you got to do is just change your formula, take the mass you were given and the velocity you just solved for, and see whether it equals the mass you were given in the previous velocity. And if it truly does, then it's conserved. I already know the answer is going to be it's not. Right? I know that energy was, finger quotes, lost somewhere along the way. I'll just do the quick math real quick here. It's 0.0149 times by that velocity squared. So I calculated on this side here 585, give or take, joules of energy to begin with. And And then 1/2 of 2.0149 times a squared. On the other side, oh boy, I got 4.3 joules of energy on the other side. Anybody else calculate those numbers too? Yeah. So on the left-hand side, I calculated 1/2 of mv squared being about 585 joules. And on the right-hand side, I got 4.3 joules. Does that actually make sense? I think it makes a ton of sense because we lost energy due to sound, heat, warping and breaking of materials. So it actually makes sense that we lost our kinetic energy. The kinetic energy just went to other formats. Okay, now I think I can wrap up. So here's what we learned today. We learned about elastic and inelastic collisions, a little more vocabulary, but we also discussed the idea of problem solving and how when you're problem solving some of these equations, you have to take a big picture approach. Rather than just plugging numbers into just one random formula and just solving for the isolated variable, sometimes you have to make your own formulas, and that's challenging. Okay. So this leads into my last little idea, and then we'll take off here. If you guys have finished the first assignment, that's fantastic. To be honest, the first assignment is very basic. It's more or less what I just described, the idea of here's a formula, plug in all the numbers but one and solve for the remaining one. Okay. The second assignment, if you guys are ready to start looking at it, only has 4 questions on it. That's it. And the 4 questions, though, are much more involved because they're very much more scenarios. And you have to figure out how to apply and problem solve them. And so I'm going to mark the second assignment. You guys can go ahead and mark your first assignment because the answer key is online. The second assignment I'm going to mark, and I'm going to mark it according to the written response rubric that's on the course outline. So maybe I'll talk about that more tomorrow because we have a work day tomorrow. But it's more of a show your work because there's a lot more, like the scenario is a little bit bigger. It's not just F delta T, M delta V, plug in 3 out of 4, solve. Right? It's going to be a scenario. Okay. But you only get 4 though. So does that make sense? So anyways, tomorrow there's 2 things to work on then. I'm not going to steal your time anymore tomorrow, but tomorrow you can start working on your lab and work on that some more, and you can start working on the second assignment. And then on Wednesday, we're going to do another lab. So, sound good? Cool. If you guys want to, you can take off. If you have questions,